All right. Hey, everyone. I just want to go over the 3.3.5 practice just because a lot of people had questions about this, and I felt like the text online was not super clear when it taught some of these concepts. So I'm just going to go through this and help either explain some of this or at least tell you where to find the answer in the text. The first thing, electron configuration. I don't like the way the text taught this topic. Okay, so I'm going to try to explain it more clearly. Okay, if you think about electrons, so imagine this is the nucleus, then we have the first energy level, the second energy level, the third energy level, the fourth energy level. And you may have in past science classes known that the first energy level can hold 2 electrons. The second energy level can hold 8 electrons, okay? And then the third energy level can hold even more than that. And you kind of, depending on how many electrons you have, you like fill up the energy levels, okay? So the first energy level can hold 2 electrons. The second can hold 8. The third can hold 18. And the fourth can hold 32. And it gets bigger and bigger as you get further from the nucleus. But I just want to teach you the first 4 energy levels. The thing is, these levels don't fill in order. You don't just fill this, you fill the first, you go to the second, you fill the second, you go to the third, but you actually only put 8 in the third level, and then you jump up to the fourth and put 2, and then you go back to the third, and things start to feel very out of order. So it's not as simple as it looks. And the reason for that is that these energy levels are divided up into sublevels. Okay, so the first energy level has one sublevel called 1s. The second energy level has 2 sublevels. One of them's called 2s and one of them's called 2p. The third energy level has a 3s sublevel, a 3p sublevel, and a 3d. Okay. So it's first energy level, second energy level, third energy level, and the fourth energy level has 4 sublevels. Okay, you can kind of see a pattern. 4s, 4p, 4d, and 4f. Okay. But these levels don't fill in order. Okay, you don't just fill 1s and then 2s, 2p, 3s, 3p, 3d, 4s, 4p. They start to fill out of order. Okay. The number of electrons that can go in each sublevel, 1s can hold 2 electrons, 2s can hold 2 electrons, 2p can hold 6, 3s can hold 2, 3p can hold 6, 3d can hold 10, 4s can hold 2, 4p can hold 6, 4d can hold 10. You might see a pattern here. 4f can hold 14. Okay, so if you add each level up, this can hold 2, this adds up to 8, this adds up to 18, and this adds up to 32. So you can see all the sublevels add up to the total number of electrons. Okay, again, the tricky part is that they don't fill in order. Okay. We do start with 1s when we're filling the sublevels, and then we go to 2s, and then we go to 2p, and then we go to 3s, and then we go to 3p. So far, so good. But the thing is, you actually jump up to 4s next. And then you go, I'm going to go down here. After 4s, you go back to 3d, then you go to 4p, then you go to 5s, and then you go back to 4d, ... You don't need to memorize that. I'm just trying to show you how the sublevels don't fill in numerical order like you would hope. Okay. The order that they fill in, though, is embedded in the periodic table, which I will show you in a second. But what we do, if you could go down to C on 3.3.5, okay, on the first page, what they're showing here, and I'm going to tell you the answer to C because it's not very clearly described in the text, is each sublevel, okay? So this is the first energy level. This is the 1s sublevel, and each arrow is an electron. So there's 2 electrons in the 1s sublevel. Then this is 2s, and this is 2p, okay? So the 2s has 2 electrons, and the 2p has 6 electrons. Like we said here, 2s has 2, 2p has 6 for a total of 8 in the second energy level, okay? Then we're going on to the third energy level. This is 3s, 3p, and 3d. And then this is the fourth level, 4s. And they didn't go beyond that. 4s has a p, a d, and an f, but this element doesn't have anything that's that high, okay? So what you can see is they put 2 electrons in 1s, 2 electrons in 2s, 6 in 2p, 2 in 3s, 6 in 3p. And then they jumped up to fill 4s and then went back and put the rest in 3d. Okay. So the way we would write this electron configuration is 1s, and then we would put a 2 up high, indicating it has 2 electrons, 2s2, 2p6, 3s2, 3p6, and then after 3p, we filled 4s with 2, and then we went back and filled 3d with only 3, okay? And vanadium has an atomic number of 23, which means it has 23 electrons. So if you add up all those little numbers tell you the number of electrons in the sublevel. They all add up to 23, okay? So this is the answer to A, okay? This is the answer to A. Another way you could figure it out is I emailed everyone a reference sheet. I think this is a really good printout that takes a lot of the charts and puts it all in one place. Okay, so I think if you print out this reference sheet front and back, it will be really helpful. One thing I included on the back was their electron configuration table. Okay, so what you can see is that you can kind of trace this until you get to your element, and it'll tell you which sublevels you need to fill. Okay, so if we were trying to get to vanadium, which is right here, okay, we would start in the first row. 1s has 2 electrons. That's 1, 2. 2s2, 2p, 1, 2, 3, 4, 5, 6. Okay. 3s2, 3p6. And you can see after 3p down here, we go to 4s, 1, 2. And then this area right here is 3d. So 3d1, 3d2, 3d3. So each square on the periodic table represents an additional electron being added, okay? Vanadium has 23 electrons because its atomic number is 23. So you can just kind of count your way over up to the number 23 and figure out the electron configuration. So that's why I put this here. So this is an easy way you can go, okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. So whatever element you're looking for, just trace your way up to it. For the noble gas electron configuration, this was on in 3.1.1, page 19. Essentially what you need to do is take your element and count backwards until you get to a noble gas, which is the last column, okay? So vanadium, we're going to count back, titanium, scandium, calcium, potassium back here, okay? So I go back, and I stop here. Argon. Okay, argon has an atomic number of 18. So this was my vanadium. Go back 22, 21, 20, 19, 18 until you get to something in this column. I'm going to use argon, the noble gas, to replace the first 18 electrons. Okay, so my answer to this was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. That was the full electron configuration for vanadium. I got it from this. I also got it by looking at this, okay? Now, if we were to turn this into the noble gas configuration, you count backwards, okay? Count back until you get to something in the last column, argon, number 18. I'm going to use that to replace the first 18 electrons, okay? So I'm going to underline the first 18 electrons. This is 2, 2, 6. All right, that's the first 18 electrons. So instead of writing all of that, I'm just going to write AR in brackets, okay? And then I'm going to add on the extras, 4s2, 3d3, okay? So argon replaces the first 18 electrons, and then we added on 2 more and 3 more for a total of 23, okay? Because people just get sick of writing 1s2, 2s2, 2p6 over and over and over again. So we replace all those inner core electrons with the noble gas and then just add on the extra. Okay, so again, that's detailed on 3.1.1, page 19. All right, so hopefully that clears some stuff up. This next stuff for question 2, A is 3.1.3, page 6 to 8. B is 3.1.3, page 13 to 16. C is 3.1.3, page 17 and 18. And D is 3.1.3, page 11. So that's where you find those in the text. And then question 3, you'll find this in 3.2.1, page 6. And then the intermolecular forces, you'll find all of this in 3.2.3, 3.2.3, and 3.2.3. Okay, that was all of question 4. And then all of question 5 you'll find in 3.3.1. That's where you'll find the answers to all these. Question 6 you'll find in 3.3.1. Question 7 I'm going to go over because I don't think it was explained very clearly in the book. This is in 3.2.1, page 22 to 23. So what they're talking about is Lewis structures. Lewis structures show the valence electrons only, okay? Valence electrons are the electrons in the outermost occupied energy level. So as you learned, each column on the periodic table, all these elements have the same number of valence electrons, okay? And so I put it down on this periodic table at the bottom to make it easy. Everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Everything in group 3 has 3, group 13 has 3, group 14 has 4, group 15 has 5, group 16 has 6, group 17 has 7, and group 18 has 8. So just looking at the group that something's in on the periodic table can easily tell you the number of valence electrons it has. So draw the Lewis structure for the Se and 2H atoms, okay? So we have Se, okay? Se is right here, okay? It has 34 total electrons, but the valence electrons are the only thing we include in the Lewis structure. So if you look down at the bottom of group 16, okay, you'll see that everything in this group has 6 valence electrons, and that's the way you distribute them around the symbol. So you write the symbol for the element, and if it has 6 valence electrons, put 1 on each side, and then double up, 5, 6, and then stop. Okay, that's not supposed to be there. That was yeah, so it has 6 valence electrons, okay? And now I want you to draw the Lewis structure for 2 hydrogen atoms, okay? Hydrogen's in group 1, so they have 1 valence electron, and it wants you to draw 2 of them, like that. Okay, so that's all they're looking for 7A. For 7B, draw the Lewis structure for the SeH2 molecule. Okay, this was in 3.2.1, page 24, but I'm going to show you how I do it. So what you need to do is you need to stick the electrons that are alone, you need to stick them together, okay? So you'll notice that this side only has 1 electron and this side only has 1 electron. And that's where the hydrogens are going to latch on with their electron. So you'll have the Se again with 6. Okay. And then we have hydrogen. One of them's going to latch on here with its electron. And one of them's going to latch on here with its electron. And then the Se now has what we call a full octet. Okay, so each of the electrons by themselves is a spot where another atom can latch on and share an electron. Okay, and then for C, look at 3.3.1, page 16 is where you'll find the name of this shape. Okay, and you can just draw your own shape based on what you see on that page. Question 8, I think this reference sheet will be very helpful. Question 8 is about ionic and covalent names and formulas. So if you look back here, ionic is a metal bonded to a nonmetal. Covalent is nonmetals only, okay? And if you remember on the periodic table, this staircase right here, this staircase that extends over here, it also extends over here, separates the metals from the nonmetals, okay? So everything on this side of the staircase is a nonmetal, and I put a little note up there, including the hydrogen kind of is grouped in with these ones. And then everything on this side of the staircase and below hydrogen is a metal, okay? So the vast majority of the periodic table is a metal. So metals are to the left of the staircase, nonmetals are to the right of the staircase. So if it's a metal and a nonmetal, it's ionic. If it's all nonmetals, it's covalent. And remember, hydrogen's considered a nonmetal, okay? So that's how you can tell if it's covalent or ionic, okay? So just look at whether it has metal and nonmetal or nonmetals only. Now, in terms of naming these, if it's ionic, the name does not have prefixes, okay? So you just write the name of the first element and write the name of the second element and change the ending to IDE, okay? If it's covalent, though, the name will have prefixes. So use these prefixes to indicate how many for covalent, but you only use these for covalent. You'll never see these in ionic, okay? So that's how you write the name. If they give you the name and ask for the formula, if it's covalent, it's very easy, okay? You just use these prefixes to figure out the formula. If it's ionic, there's no prefixes to tell you how many, so you have to figure it out yourself, okay? If it's ionic, you need to crisscross the oxidation states to write the formula, okay? So manganese 3 oxide, this is a good example of one that we need to crisscross. So manganese is Mn, okay? You'll notice that Mn does not have an oxidation state written here. That's because these don't really follow a pattern. So that's why they put a Roman numeral on it, is to tell you the oxidation state. So manganese 3 has an oxidation state of 3+. Oxide is just oxygen. Remember, we changed the second one to IDE. It's just oxygen. And oxygen's oxidation state is 2 negative, okay? And what you need to do for ionic is crisscross those charges, okay? And then drop the plus and minus. So the 2 comes down here and the 3 comes down here. So it's going to be Mn2O3, okay? Because basically we need enough MNs and enough O's that the charges all add up to 0, okay? With 2 MNs, that's 3 plus and 3 plus, and 3 O's, 2 minus, 2 minus, 2 minus, all of that adds up to 0. So the charges have all canceled out, and this is our answer, okay? But for something like this that's covalent, you don't have to do that. You just look at the prefixes to write the formula, okay? All right. So that is it for 3.3.5. Hopefully that is helpful.